Okay, so next question we're going to ask ourselves is, what is a relation? This has been hinted at a little bit already in terms of I said that I talked about transitivity in terms of subsets, but a relation on a set S is a function that takes two inputs from that set, so A and B, and then just spits out a yes or no answer. So there's, and we're normally going to write it something like A R B. If the answer is yes, then A R B, or A relates to B. There's lots of examples of this. So already said the subset relation, then shares both parents with, shares one parent, less than or equal to, strictly less than. And then I can also, one good way for manufacturing these is to do, come up with a graph. And the relation has an arrow too. So let's look at the first thing we're going to want to look at here is, let's check out transitivity. So which of these guys would have the transitive property? So the transitive property is, if A relates to B, then B, and B relates to C, then A also relates to C. So to give an example, less than, strictly less than, is transitive. If 4 is less than 6 and 6 is less than 8, then 4 is less than 8. Another example is shares both parents. Shares both parents here. So me and my brother Declan both share parents, so we relate to each other in that way. But if you have a half sibling, then so if Connor and Dan are half brothers, then they do not share both parents, but they do share one parent. So the question would be then, is this a transitive property? No, because Dan could have, if, let's say, let me change names here. So father 1 has a child with mother, and then the mother has two. So then these guys have child 1, these guys have child 1, 2, and then these guys have child 2, 2. On the relation that of share one parent, then we would have these guys relate and these guys relate, but these guys do not relate. So share one parent is not a transitive relation, but the subset relation, as we already talked about, is a transitive relation. Less than is a transitive relation. Less than or equal is a transitive relation. And shares both parents is a transitive relation. And I can come up with either, so let's say this side is not transitive. And this side is transitive. That shares parents. both parents. I can come up with a graph such that it is transitive, like this guy up here. So we have A to B to C. Or I can come up with a graph that is not transitive. So, oh, sorry, this actually is not transitive right here. But if I draw that line in there, then it is transitive. But A to B to C, A for this guy does not have an arrow, therefore it is not transitive. But here, A does relate to C because A has an arrow going directly to C. And if you go down the line, that's everything that B relates to as well. So reflexivity is another useful property. So this means that that all of the elements in your set relate to themselves. So for this guy, one of the most obvious examples that we already talked about is less than or equal to. So that is going to be reflexive, but strictly less than is not, because 2 is not strictly less than itself, but 2 is less than or equal to itself. Shares both parents, shares one parent, you share at least one parent with yourself. Born same year as. Born within 5 years of. Going back to the transitive question, this would not be transitive because if my older brother is 4 years older than me, and then we had another older brother who is 4 years older than him, then I would relate to the middle brother, but not to the oldest brother, despite the fact that my middle brother would relate to both of us. So reflexive, some more examples of not reflexive. If we want to do the graph here, has an arrow to. This guy is not reflexive, but this guy is reflexive. Symmetric. So symmetric, born within 5 years of. That is a pretty clearly symmetric property. If I was born within 5 years of my brother, then my brother was also born within 5 years of me. Born same year as. Shares both parents. Shares one parent. What else is symmetric? Lots of things will end up being symmetric. If I wanted to generate a graph that has this, then the simplest interesting one would look something like this. And then symmetric. So a non-symmetric would be less than or equal to, because if 6 is less than or equal to 8, then 8 is not less than or equal to 6. So that's a pretty clearly non-symmetric example. To give another graph, this guy is not symmetric because A relates to B, but B does not relate to A. Anti-symmetric. If A relates to B and B relates to A, then A is equal to B. So less than or equal to is kind of the go-to example for this guy. For this guy, if 6 is less than or equal to 6, so if A is less than or equal to B and B is less than or equal to A, then we know that A is equal to B. So this is the most common example of this. I could come up with some graphs here too if you want, but they won't be particularly interesting for this guy. Maybe I should name them differently, but most of the relations that we've talked about so far have not been anti-symmetric. So shares parents with both parents, shares one parent. These guys are both not anti-symmetric. It's a little bit weird using these two different negatives, but that's what it is. Born same year as. If I'm born the same year as Colette and Colette is born the same year as me, that does not mean that I am Colette. So one of the things that we care about for this is that it can, an equivalence relation is a relation that is transitive, reflexive, and symmetric. Spell arithmetic. Yes, arithmetic. Okay. So some of these examples already listed. So arithmetic equivalence is the only one that we haven't talked about, but if 1 plus 3 is equal to 4 and 2 plus 2 is equal to 4, we can clearly see that 1 plus 3 is going to be equal to 2 plus 2. 1 plus 3 is going to be equal to itself. Any number is going to be arithmetically equal to itself. So it's reflexive, it's going to be transitive, and it will also be symmetric, that 1 plus 3 is equal to 4, therefore 4 is also equal to 1 plus 3. So that is shares both parents with is also going to be an equivalence relation. And then we can come up with a bunch of graphical examples. But something that's interesting to think of is that this can break up a set into different what are called equivalence classes. That means that they are equal under this relation. So if I want to look at and then L and T. These are some of my cousins on my mom's side. So if these guys are me and my two brothers, these are my cousins Colette, Kieran, Mairead, and these are my cousins Grania, Liam, and Kathleen, but I won't have T because C and K were already taken. So these guys are equivalence relations under the operation of has the same parents or shares both parents. That this is a way that breaks up our whole set of actually only about half of the cousins, but I don't feel like writing out almost 20 of us. So that is a way to break up our whole set into 3 distinct subsets such that there is no overlap between the 3 of them. Another thing is we can do the equivalence class of everything that adds up to 4, everything that adds up to 5, and everything that adds to 6, etc. So adds to arithmetic equivalence is an equivalence class that it breaks down. So if I have a graph equivalence class, then see. And then you go there. Cool. And then we'll do D, E. These guys both have to relate to themselves. So this would also form an equivalence class. Equivalence classes, these might seem kind of ad hoc and thrown together, but equivalence classes do pop up a lot all over the place.